did this. So this one kind of covers several of the things that we covered last week, dealing with our triangles and circles. What I want you guys to do is, based on this circle having an 8-inch radius, and this angle over here being 20 degrees, find the area of this sector. Now this might take a second. We can discuss it amongst each other a little bit if you want to. Remember, there's two pieces of information you need. You need the area of the whole circle, and you need the central angle. Now I'm going to pause this and first step, what's the central angle have to be? 40. How do we find that?
Take a look at the cutout piece, not just the darkened piece, but all of it.
Yep.
It's like two different triangles.
You got it.
So with that being a 20-degree angle,
Yep.
with the type of triangle it is, you know the other angle is exactly opposite from it, needs to be 20 degrees as well.
Perfect.
You take 40 from 180 and you get the angle at the corner.
Yep.
And then you take that and subtract that from 180 because the straight line across is 180 degrees.
Perfect. Yeah, any triangle that is formed in a circle with one of the vertices at the center and the other two on the circle is going to have to be an isosceles triangle, because these sides are radii of the triangle. They're going to be equal. So if that's 20, this is 20, making this 140, because they have to add up to 80. Then since this, of course, is a straight line being a diameter of the triangle, this has to be 40 because they want to add up to 180. Remember, we talked about that number 180 being just huge in everything we do. It appears everywhere. So now that we know that that's 40 degrees, where do we go from there? Well, we find the area of the whole circle by doing what? So pi times 8 squared, which is going to be what? 201 almost? 200.8 or something like that. 0.96. So 201 is close enough. That's inches squared. And then what? Okay. Perfect. So it's the area of the whole circle, the 201 inches squared, times our central angle of 40 degrees over 360, which is going to give us, what, 22.33 about? Sound right? You get confused, Jason.
No, I'm just looking this out.
Okay, so by popular demand, we're going to look at question 23, page 308. Which is a V-block question. Okay, so what we have here is this is 0.544 inches to the bottom of the V. Full height of the block, 2.842. This is our X. And we have a 0.800 radius. This is the dimension we're looking for. Why? Actually, no. In this one, we're given that y is 1.400, and we're trying to find x. Okay. So let's go with that. Remember, if we draw this in, that tangent there has to form a right angle to the radius at that point of tangency. So this has to be a right angle here. We're not given any of the angles. Otherwise, we know that this would have to cut this angle in half. They would cut that into two equal pieces, but we're not given that angle, so that doesn't help us at all. We are given that this is 0.8, which means we can find this distance right here because these are the two legs of a right triangle, and that is the hypotenuse. So we can do, if I call that C, a squared plus b squared equals c squared, where a is going to be the 1.4, b is going to be the 0.8, and c is that height we're looking for from the point of the V to the center of the circle, which is a very common dimension to look for in a problem like this. That's one of the things you're usually going to be looking for, is that dimension. So to solve this, 1.4 squared is 1.96. 0.8 squared is 0.64. Adding those up, we get 2.6 equals c squared, and we will have to square root. So 1.612, also generally you keep it to 3 decimal places. So square rooting this gives us 1.612 equals c. So now what we have is we have a case of, to find x, if we use the bottom of this as our reference point, as our 0 point or origin or whatever you want to call it. And you guys have done enough with the CNC now that you understand that to find missing dimensions. To find the distance between two objects, usually the best way to do it is to find the distance from a reference point to each of those objects and then find the difference. So from here to here, 2.842. From here to up here, we have the 0.544. Yep, plus 1.612. Plus, what's this last piece? The 0.8. So we got 6, 5, 19, 2.956. So that means x has to be the difference between those two. Which is 0.114. Cool. Any other questions on those, on the homework that you want me to go over? Cool. What's that?
I suppose I would have had to do my homework.
If you had done the homework, you might have had questions. Or did the right homework?
I did the right one.
Well, you did 2 or 3 homeworks. You just didn't get to the right one. Can't fault your effort, at least. One thing we saw in this last warm-up problem. This one will be slightly different. Pretend that's a circle and pretend that that's the center of the circle right there. You might have to pretend kind of hard. And this actually goes like that. There we go. For some reason, I can't draw a straight line today. But anyway, what we saw before, when this angle here was 20 degrees, this one was 40 because of the way things worked out. What would happen if I made this 25 degrees? If you look at it, this one has to be 25 degrees because it's an isosceles triangle. These 3 angles have to add up to 180, so this one ends up being 130. This one here, because those 2 add up to 180, has to be 50. What you see, because of the geometry of this, whatever these 2 angles add up to has to be this angle, because this one adds up to 180 with those 2, but it also has to add up to 180 with this one. Make sense?
Always.
Always? Always. Yes. Because of just, remember that 180 just happens to, in fact, that's a rule for triangles. Something called an exterior angle. If you have an exterior, and it's because of exactly what I just described there. This exterior angle here, this angle on the outside of the triangle, if I call that angle A, has to equal the sum of the other 2 interior angles. And again, it's for just that very reason, because inside the triangle they add up to 180 and the straight line adds up to 180. So if this is 36 degrees and this here is 62 degrees, A out here has to be 36 plus 62 or 98 degrees. What that means inside our circle here to review some vocabulary, this angle, if you recall, was called a central angle. Makes sense. Its vertex is at the center. This angle was called an inscribed angle because its vertex is inscribed on the circle. Remember, an angle or a vertex that's on the circle is an inscribed. Even when they're not set up like this, the relationship is the central angle is equal to 2 times the inscribed angle. Now that doesn't mean any central angle and any inscribed angle. You'll notice what's special about these two angles is they come out here and they intercept or they identify the same arc. That's called the intercepted arc. So whenever we have a central angle and an inscribed angle that intercept the same arc, that central angle will be twice whatever the inscribed angle is. So let's say that this is a 110 degree angle. What's this over here have to be? 55. Very good. I went the other directions. That has to be half of it. Notice it doesn't even share a side like we did before. It doesn't matter. What's this angle here going to be? 55 degrees. It's still an inscribed angle on the same arc. What's that angle have to be? Still 55 degrees. Even though it doesn't contain the center, it cuts off to the side like that, it's still an inscribed angle on that same arc. The arc then, remember the length of the arc itself depends not only on this central angle, but also the radius of the circle. Well, to take the radius out of the equation, we can also describe that as just a 110 degree arc. So what we're doing is we're defining that as a certain fraction of the circle. That's a full circle is 360 degrees, so we're defining that as 110 3/60ths. So let's say we have an 80 degree arc out there. In other words, an 80 degree central angle. We've already defined well, the inscribed angle has to be what? Half of that, 40 degrees. There are other angles that can be formed off of it. For example, this angle here that is formed with a tangent. Now remember, we know that this tangent would have to form a right angle to that radius, correct? Do we know anything about this angle right here? Well, this is an isosceles triangle, isn't it? If this is 80 degrees, these have to each be 50, don't they? What's this angle over here going to have to be then? 40. That's still a right angle on this side, isn't it? Has to be 40. This math will always work out this way. Even though this is a tangent that forms one side of this angle instead of two chords. Remember, these are called chords here. Even though this is a chord and a tangent rather than two chords, this angle here, its vertex is still on the circle. It is still basically an inscribed angle. It's called a tangent angle or tangent inscribed angle. But that angle is still going to be half of that intercepted arc. Since that is an 80 degree intercepted arc, this is a 40 degree angle. Pretend that touches there. So, if this angle right here is 52 degrees, can I find this angle here?
Yes.
Tell me how then.
I use yes or no question.
You're just taking a guess to see if you can.
Taking a wild goose guess.
Is it possible? Well, it might be. I don't think I gave you enough information, to be honest. But what can we find out? What do we know from the 52 degrees? Well, we can find this angle. Why can't we find that one? 90 degrees right there. So that has to be 38 degrees. What else does that tell us? Oh, we know the other side's 90. Yep. Do you know anything about either of those two angles? No, unfortunately it doesn't. What if I were to throw in this little piece of information right here to tell you that that intercepted arc over there is a 100-degree arc? Does that now help?
Yeah.
Oh, yeah. That would help a lot. And actually, it can't be a 100-degree arc. Let me bump that up a little bit. Let's call it a 140-degree arc. That'll fit scale a little bit better. Now, what does that tell us? If we look at this, this is an inscribed angle on a 140-degree arc. So this angle here has to be how much? 70 degrees, half of the 140. So how does that help us get to this angle over here? Well, 70 minus 52 would give us this angle, but that doesn't do a whole lot. We can find this one over here, because these three have to add up to 180. We got 70 and 38 makes 108, correct?
Mm-hmm.
Means that 72 degrees is this angle right here. How does that help us? If that's 72, what does this arc out here have to be? $144, because the angle is half. That angle has a vertex on the circle. It's a tangent angle, but it's also an inscribed angle. It's half of the intercepted arc, so that's a 144-degree arc. How does that help us get back to here? Yeah, that's an inscribed angle on a 144-degree arc, so that's has to be half of it. So 72 degrees. See how fun that is? Kind of like a big old puzzle, isn't it? Your head hurts? Stick with me.
I have a question.
Yes, sir.
With that 70-degree angle that we figured out for
Yep.
53, we took the 52 minus the 7, or the 72 minus the 52.
28 degrees here. Yep, you get the 28 degrees over here, yep.
Okay. Would that triangle not help us figure out that other angle?
Well, that would mean this could be 28 degrees, which makes that 56, which would make this 144. Or no, that wouldn't be 144. What would that be? It'd be 124, wouldn't it? Something doesn't work out there, does it? That'd be 180. This is 18, not 28. That's why. That's better. So that's 18. So that'd be 36. So that would be 144 degrees. I can't subtract.
To me, it cuts out some of the steps.
It might, yeah. And that's the thing with these problems is you can, just like you said, you can either work them through triangles like that, or you can work them through the circles and the arcs. Most of the time, there's 4 or 5 different ways to get to the answers. Yep.
Depends on how you look at the problem.
Yep. And to me, since I'm talking about circles, I'm thinking in terms of circles right now, so that's what I'm seeing. But depending on your mindset, and you did that last week too, you tend to see more of the triangles and the circles parts of it.
Some of it just kind of clicks for me, so something
Sure.
I stick to.
Yeah, whatever gets you there, it doesn't matter how you get there as long as you get to the right spot. So anyway,
Never even talked.
okay, let's not go there, guys. Something like this. We know that this angle and this angle have to be the same. They're what we call vertical angles. Or even if we don't have the special name for them, we know that they're both supplementary to this angle, so they're going to have to be the same. The question is, how do we use the parts of the circle and the arcs that we've been talking about to find those angles? This is what we call an interior angle. We mentioned this last week. And most of the angles we've been talking about so far are interior angles. An inscribed angle is an interior angle. And a central angle is an interior angle. But this is just a generic interior angle. To find the size of that angle, we have to use both arcs. If you think about it, if that angle were at the center of the circle, I'm just going to draw a small circle over here. If that angle, of course I can't draw a line through the center apparently. There's the center. If that angle were at the center, if those two chords intersected at the center of the circle, of course these two arcs would be the same, right? Come on. Those two arcs would be the same and there wouldn't be anything to deal with. That each angle would just equal the arcs. If the angle was inscribed like that, if the vertex was at the side of the circle, of course this arc over here would be 0, and this arc over here would be double the angle. So we know that whatever these angles are, they're between 0 and whatever the largest one of those arcs is. As the angle gets closer to one side, the smaller the one arc gets and the larger the other one does. To combine them, and there is a proof of this, I'm just trying to figure out how to go through the proof without totally confusing you, and I'm thinking it's best just to give you the rule. To combine these two arcs, let's say that this arc over here is 58 degrees and this one here is 46 degrees. That angle has to be between those two arcs. In fact, what it is the average of the arcs. So that particular angle there is going to be 58 plus 46 divided by 2, which should give us, what, 54? No. 50. Yeah, 52 degrees. Here we go. There it is. For some reason, the internal calculator is skipping a beat this morning. 52. There we go.
So that is the angle.
That's this angle and this angle. The two angles that face the arcs. Of course.
I thought we said that the angle was indicative of the arc. So if
It
it was
is.
a 70-degree angle, then the arc had to be 70.
That's only if the angle is at the center of the circle.
Okay.
These angles are not at the center.
All right.
So the relationship is still there. In fact, we can use that to find an arc. Let's say that we know this angle here is 52 degrees. And I know that this arc out here is 31 degrees. I can now find my other arc. I'll call that arc X. Because I know that the average of those two arcs, if I take X plus 31 and divide it by 2, I have to get 52. Now first, before I do any calculations, does everybody see where this formula came from? Yes, sir. I average this arc and this arc, so it's X plus 3 divided by 2. And I have to get this angle. Of course, this angle is the same. It's just I only needed one of them. So now to solve this, multiply by 2. X plus 31 equals 104. And subtract 31. X equals 73 degrees. So this is a 73 degree arc. What do you think? That works. So now, of course, the closer this vertex gets to one side of the circle, the bigger this arc is and the smaller this arc is. When the vertex was right on the circle, of course, this angle ended up being half of that arc. You can think of it as being the same rule, by the way, because this arc over here is now how many degrees? 0. So let's say this is 84 degrees. Well, that angle is just the average of the arcs. 84 plus 0 divided by 2 is going to be 42. Well, we said this had to be half of the arc, the inscribed angle. So it's still the same rule. It's just a special case of it where this arc over here is 0 degrees because the vertex is right on the circle. But as we keep going with that, we keep moving that vertex over until it moves outside of the circle. This is what we call an exterior angle. Or sometimes called, do you remember what this type of a line is called that cuts through a circle? A secant. Yes, it is sometimes called a secant angle. Bless you. Because it's an angle formed by two secants. This angle, just like the interior angle that formed by two chords was earlier, is still completely defined by these two arcs. Now remember, we said if it was on the circle here, this angle would be half of this arc. Well, as we move outside the circle, does that angle get smaller or larger? It's getting smaller. It has to be less than half of this arc. But as we move outside the circle here, does this angle get smaller or larger? Or this arc? This arc would actually get larger. So the larger that this arc here gets, the smaller the angle is. And the relationship we come up with is, if I call this arc X and this arc Y, this angle over here is half of the difference between the arcs. So let's say that this arc out here, X, is going to be 72 degrees, and this arc in here, Y, we're going to call it 24 degrees. Our angle will then be 72 minus 24 divided by 2. Well, 72 minus 24 is 48, divided by 2 is 24 degrees. So this angle out here ends up being 24 degrees. Let me do another example that isn't quite so confusing because we have the same numbers appearing way too many times there. Okay, so this angle out here is going to be 148, or this arc out here, sorry, is 148 degrees from here to here. This arc here, I'm going to call it 52 degrees. So to find this angle, talk me through it. Okay. 148 minus 52 is 96. Divided by 2 is 48 degrees. So this is a 48 degree angle out here. So now that we are having loads of fun with our circles. Oh yeah, you are. You know you are. We're going to see if my artistic ability can handle this. So that's a diameter. This is a tangent. That's another tangent to that radius. Try not to make this too complex for you. Doing a wonderful job of keeping it simple. I figured I would. That's a right angle there. Let's see what I want to give you. I'll tell you that this arc here is 70 degrees. I'll tell you that this arc here is 120 degrees. I'll tell you, this angle out here is 30 degrees. And let's see, the radius is 3 centimeters. I already told you those are perpendicular. And I'll give you that this length right here is 2.5 centimeters. First thing I'm going to ask you for. What is the length from here to there? Yeah, that's just the diameter. 6 centimeters. Now, if I were doing this on a quiz or a test, I might label this, point B and point D or whatever, and I might ask you what's the distance from, or what is BD? The distance from point B to point D. Same thing. Let's see, the next thing I'll ask you. What is this angle right here? What's that? Well, if I were to cut this across here, like that, what's this angle here have to be? Well, first of all, what's this angle here have to be? 15, half of the 30. This is 90, so this one's going to have to be 75. Where did 75 come from? Yeah. 90 and 15 make 105. 180 minus 105 is 75. If that's 75 degrees, what's this one? Say 75. Because this triangle and this triangle better be the same, right? Oops, where'd I go? Get back here. It's running away on us. So now, that's 150, which means this arc is 150, which means this arc is 30, 180. It's half a circle, be 180, right? Now, excuse me, this angle is the one I'm trying to find, formed by these two sides. This total arc is 120 plus 30 is 150. So that has to be 75 degrees, half of the 150 degree arc. See how easy that is? It is, well, it's not quite obtuse. Let's see what else. How about this angle right here? Can we find that one? Right there. Well, do I know this arc from here to here? What is it? Why is it 60?
Because it's 180 minus 140.
Yeah. This is a diameter, which means that this has to be 180. So if this is 120, this has to be 60. Add up to 180. If that's 60, do we know this arc from here to here? No. We know this part's 30. Do we know this piece? Yeah. Well, the 70 degrees, though, is... Okay, yep, 70 degrees is its arc. Okay, so that's 100, and this is 60. Come on. So 100 plus 60 divided by 2 for the central angle, remember? So that's 160 divided by 2 equals 80 degrees. So that is 80 degrees. See, we're moving right along. Let's see, where's... Oh, come on. Oh, I'm trying to find another tough one here. Yeah. Oh, here's one for you. How about the arc from here to here? This one's actually pretty easy. It's just a matter of remembering what the rule is and seeing it. Remember, this here is a chord, right? And since it is perpendicular to the radius, or diameter in this case, it cuts this in half. So this would have to be 60 as well. See all these things coming together?
No.
It's tough. Okay. Well, the good news is there's going to be plenty of practice in your homework tonight.
Oh, cool.
We had another packet, or
No, this should be in the same packet.
I don't remember what packet that is.
I believe it's in the same packet, page 315, 1 through 26.
He says unit 49.
On the front? Okay.
Is it unit 49 on this one?
Yeah, unit 49.
Okay, it is. I was thinking we're beyond that.
315.
What was the one that you gave us in that packet for,
It started on page 305, up through page 308.
what?
Yeah, page 315 is still in this packet.